Hello, everyone. So in this BSF Speakers Corner talk, I'll present our recent work, which is Josephson-Current signature of Unpaired Floquet Majorana bound state. I'll start with my introduction. My name is Rekha Kumari. I am a PhD student at Indian Institute of Technology, Kanpur, India. And I'm doing my PhD in supervision of Professor Arijit Kundu from Indian Institute of Technology, Kanpur, India. And this work has been done in collaboration with Professor Kundu and Professor Babak Seradjeh from Indiana University, Bloomington, United States of America. So I'll start with the outline, starting with the short introduction to Majorana Fermions, and then short introduction to Floquet Majorana Fermions. And after that, I'll talk about the transport signatures of Majorana Fermions. Basically, when the system is having the Majorana Fermions, there are two transport signatures. One is the quantized zero bias conductance, and second is Josephson-Current signatures of the Majorana Fermions. And then I'll talk about the transport signatures of Floquet Majorana Fermions, like what do we expect and what is different. And then to understand it more, we'll talk about the occupations and some rules of these Floquet Majorana Fermions. So the Majorana fermions are the particle hole symmetry related states of positive and negative energy excitations in superconductors. And a Majorana state is equal mixture of the particle and hole-like excitation, and thus topological protected zero energy mode of superconductor. And the 1D topological superconductors host such Majorana-like states as age modes. So if we write the Majorana operator, which creates the Majorana state like gamma dagger, so and the other operator which annihilates the state, and we write the operator for that gamma, then for the Majorana fermions there is an equality which in which like gamma dagger E is same as gamma minus E. And the Floquet Majoranas are basically the Majorana modes in periodically driven system. So when we derive the system, the parameters of the system as a time periodic function, so that the Hamiltonian of the system is a periodic function of time. The physics of those kind of systems is given by the Floquet states, given by this expression, where psi alphas are the Floquet states and epsilon alphas are the quasi energies. It takes values from minus pi by 2 to minus pi by t to pi by t, and u alpha t's are the time periodic Floquet modes. So similar to the static case, this system also have the zero energy Majorana modes in the topological phase. And on top of that, there are also the other kind of modes called pi Majorana fermions, which are at the edge of this Brillouin zone boundary. These are also the Floquet modes, the topological Floquet modes. So now, to understand this Majorana mode, physics of the Majorana modes further, I'll define a Hamiltonian, which is like the 1D Kitaev chain having the n number of sides. And this is expression for that. Here, the first terms represent the hopping term in the Hamiltonian, and the second term represent the superconducting gap, and the third term represent the on-site chemical potential. Now, to understand the physics of the system further, we convert the full Hamiltonian in Majorana basis using the Majorana transformation, where we decompose the creation and annihilation operators in terms of the linear combinations of the two Majorana fermions. This Hamiltonian takes this form in the Majorana basis. And in this equation, we are taking the choice of parameter in which t is same as delta. So there are two terms. One is the delta dependent and the second is the chemical potential dependent. And now the effect of the second term, which is the chemical potential dependent term, is that like the two Majoranas, like we decompose the creation and annihilation operator in terms of the Majorana modes. The second term basically couples those two Majorana fermions again, and in this term, two Majoranas which are like on the same site are connected. Wherein the first term, which is the delta dependent term, It connects the Hamiltonians, it connects the Majorana modes from two different sites. If this is a site 1, this is a site 2, then the one Majorana mode of site 1 is connected to the second Majorana mode of site 1. So in this phase, the system is in trivial phase because there is no difference in the system, like no difference between the bulk and the boundary of the system. But in this case, the system is in the topological phase, where at the boundaries there are two distinct separated Majorana modes. So from this, we understand that the system is having two phases, like phase 1 when the mu is larger than the delta or t, where the system remains in the trivial phase because this term dominates. And in phase 2, when delta equal to t is larger than mu, the system goes to topological phase, in which there are free Majorana modes at the boundary of the system. To understand it more, we define the basis to diagonalize this Hamiltonian given by the dj and d operators, which are basically the linear combination of these Majorana modes in the topological phase of the system. And we find the entire Hamiltonian can be written in the eigen basis. And in this eigen basis, there is the first term, which is basically for this part of the system. And the second term represent the free fermion, which is the linear combination of the two Majorana fermions, which are localized at the different ends of the superconductor. Now, if the system is having this kind of zero energy topological protected Majorana modes, then what are the transport signatures of it? To understand this, the first transport signature is quantized zero bias conductance, in which if we connect the one Kitaev chain when it is in the topological phase having the Majorana mode at the boundary, and we compute the conductance, zero bias conductance, then we find the system shows the quantized conductance at zero bias having the value 2e square by h. And this is the signature for the static Majorana fermions. This work has similarly, when the system is having the Floquet Majorana fermions, what are the signatures? To explain this, I'm taking the reference where this work has been done by Professor Arijit Kundu and Professor Babak Seradjeh. And they find when the system is having the Floquet Majorana modes, instead of the quantized conductance signatures, there is a signature which shows the summed conductance is quantized. And in the summed conductance, they are defining this quantity as a summed conductance, where V is the bias in the system, and n omegas are the different Fourier harmonics of the frequency. So by summing over this n Fourier index, they find the conductance when the system is having the zero modes or the pi modes is quantized, and the value of it is 2e square by h. So this is the signature, which is like the first signature when the system is having the Majorana fermions or Floquet Majorana fermions, the conductance or the summed conductance is quantized. And the second signature is basically the Josephson-Current signature. So to explain it further, I'll first define the Josephson effect. So Josephson effect is basically when two superconductors are connected through a weak link, then there is a current flow across the junctions, and the current is carried by the Cooper pairs having the charge 2e. So now if the system is in the trivial phase, then the Cooper pairs carries the current. But when the system is having the topological phase, like these two superconductors are in a phase when these two superconductors are in a phase when there are free Majorana and modes at the boundary, then in this case the current is carried by the Majorana state, which for the Majorana states, this is the state formed by these two Majorana modes. It has the charge E, effective charge E. And This is is the one way one can differentiate the system when it is having the Majorana modes and when it is not having the Majorana modes by the trivial Josephson effect and the topological Josephson effect. To understand it more, we take the second case when the system is topological and two superconductor with different phases phi L and phi R connected through a weak link, and we write the Hamiltonian when alpha equal to L. This equation describes the left superconductor having the phase difference phi L in the topological phase, because we are taking the mu to be 0 and t equal to delta. And when alpha equal to R, the second superconductor, this gives the Hamiltonian of the second superconductor having the phase difference phi R. Now, this H alpha gives the Hamiltonian of this part and the Hamiltonian of this part. Now, we define a tunneling Hamiltonian which connects the last site of the first superconductor with the first site of the second superconductor by this. Here, this omega j is just the tunneling parameter. And when we compute the using the Majorana transformations, again, when we compute the effective energy of the system, we find in the topological phase, it takes this form where the effective energy is a function of cos phi by 2, and it depends linearly on the coupling parameter. And this D is the fermionic state which is formed by the linear combination of these two Majorana modes which are localized at the Josephson junction. Now, there is one important factor. Till now, we were discussing about the case when the Majorana modes were exactly at the zero energy. We find in the static case, when the energy of the edge modes at the junction is not exactly zero, it is plus minus delta, where this delta depends on the system sizes of the superconductors. It vanishes exponentially as their separation increases. And when we connect those two superconductors, which are having the Majorana modes at energy plus delta minus delta instead of zero, they hybridize in presence of the small coupling, and the effective energy changes by this. Now, when we compute the Josephson current, in the static case, the current operator is given by this expression, where this F effective is the Fermi functions, are the Fermi functions of these effective energies, and these are the phase derivatives of these effective energies. And we get this expression. And now, to understand it further, like how these gaps plus minus delta changes the signatures of this Josephson current, we plot the expressions in two limit. In the limit one, when delta is much larger than omega j, we find the entire the expressions with the E effective and J, the current expression can be written in this form, and current shows a 2 pi periodic nature. So this is the E plus, as a system is particle hole symmetric, the energy states always comes in a pair. So if there is a state plus E, then there is also one state having the energy minus E. So this is the plus E state, this is the minus E state, where E is cos phi. And when we compute the current, we find the current depends quadratically on the coupling parameter, and it shows the 2 pi periodic nature with respect to the phase difference. Phi is a phase difference, which is basically phi R minus phi L. Phi R is the phase of the right superconductor, and phi L is the phase of the left superconductor. And in the second case, when omega j is much larger than delta, we find the effective energy of the system can be written in terms of cos phi by 2, and current depends linearly on the coupling parameter, and it depends. It is a 4 pi periodic function of phase difference. So, in the difference between these two limits are like in this limits. The physics of the current is basically carried by the Majorana fermions. And similarly, if we write the current expression, we find using this formula, as the system is particle hole symmetric, one can write this expression in terms of this, where delta n is the difference in the occupation of this plus E state and minus E state. And in the zero temperature limit is basically -1 because the occupations are given by the theta functions. And the 4 pi periodic signatures of the current when the system is having the Majorana modes, it reflects in terms of this sharp current switchings as phi equal to pi phase difference, because the system always selects the minimum energy state. So there's the interchange in the occupations at phi equal to pi phase difference. So what do we expect? From this analysis, we expect, okay, when the system is having the static Majorana fermions, the current should be a 4 pi periodic function, which shows like the sharp switchings at phi equal to pi phase difference. And also it should depend linearly on the coupling parameter. So now to check this, like whether the same signatures are there for the case of the Floquet Majorana fermions or not, we define, we take the time periodic Kitaev model, and this is the phase diagram of the system. And we start with the phase when the system is having, we start with the phase when the system is not having any kind of topological mode. And when we drive the system, we find the system goes from trivial to topological phase, and in the topological phase there are the pi modes and or as well as this zero modes. And we also find the localizations of this Floquet Majorana modes depends on the system size. Like in this plot, we are plotting the quasi energy gaps of the Majorana modes with respect to the system size. And we find by increasing the system size, one can go from a region in which delta naught is much larger than omega bar j to the region where delta naught is much lesser than omega j. And so we expect this signature should also be controlled like by the system size controls of this junction, similar to the static case. And to understand it further, we compute the current using the non-equilibrium Green's function techniques for the different system sizes. So this is a system current. Okay, so in this plot, this y-axis is the current. And the x-axis is the phase difference. In this plot, we are again the gaps of the Majorana modes with respect to the system size. So we are selecting the system size n equal to 35, which is somewhere here. Delta naught is greater than omega bar j. And we find the current doesn't show the 4 pi periodic nature, and also it depends quadratically on the coupling parameter. This is similar to the static case. Again, we take the second system size, which is n equal to 45. So two superconductors having the 45 sites in each are connected through a weak link. This is the Josephson junction in this case. And we find the current goes from some 2 to 1, but again in the small coupling limit, it depends quadratically on the coupling parameter, and also it doesn't shows any sharp jumps at phi equal to pi phase difference. Then we select the next system size, which is n equal to 55, somewhere near this boundary when delta naught is almost equivalent to omega bar j. And we find, okay, it start decreasing like from the quadratic dependence to it goes to the linear dependence on the coupling parameter. And also it starts showing this the sharp switches at phi equal to pi phase difference. And then the last system size n equal to 75, which is somewhere here, in which like delta naught is much lesser than omega bar j. We find current depends linearly on the coupling parameter, and it shows the sharp jumps at phi equal to pi phase difference. So we understand the steep jumps of the current, which is the reminiscent of static Majorana fermions mediated Josephson junctions, depends on the system size and quasi energy gaps, and the jumps. These jumps at phi equal to pi phase difference get steeper and steeper, and current also becomes linearly dependent on the coupling parameter by increasing the system size, because the gaps of the Majorana fermions, it decreases. Now, to understand these signatures further, we were having the questions. Okay, so similar to the static case, like in the static case, current can be written in the effective energy derivatives multiplied by the corresponding Fermi functions, which gives the weight occupation of this state. And as the system is particle hole symmetric, this can be written as a delta n. Delta n is the occupation difference times the derivative of the if this E minus with respect to the phase difference. And now the question comes, like, can we get some similar expression for the case of the Floquet-Majorana fermions, in which the current can be written like the quasi-energy derivatives of Floquet-Majorana fermions and some occupations of the Floquet-Majorana fermions. And if there exists this kind of expression, then what is the difference in this driven case? So to understand it, we compute the steady state occupations of the Floquet states, in which we define a system where one periodically driven Kitaev P-wave superconductors is connected by the reservoirs in a weak coupling limit. And in the system, we define the steady state density matrix in the basis of the Floquet state given by rho. So here U alpha and U betas are the time periodic Floquet modes having the quasi energies alpha and beta. And the expression for the n alpha beta t is given by this. We are taking the lead average of this particular operator, and we find and we compute this quantity using the Floquet-Green's function techniques in the flat band limit. And the flat band limit is basically we are taking the density of states of this reservoirs to be a constant. And we find in the density matrix, like if we define a matrix which is having all the occupations, like here Q is the Fourier mode of the occupation on weight, and alpha beta are the different Floquet modes. So if we define a matrix in which the alpha beta element is given by the n alpha beta, and we sum over this Q index, then this sort of gives the all the contributions, like from the different alpha beta state when alpha is beta and alpha is not equal to beta, and similarly from all Fourier modes of this occupations. And from this quantity, when we subtract the diagonal contribution alpha equal to beta with the zero frequency term, basically Q equal to 0, so we find if we take the this difference, then this difference goes to 0 linearly with respect to the coupling to the environment. So if we take the limit rho r tends to 0, the maximum contribution comes from this. All the rest goes to 0. We also find the contributions, this function depends quadratically on this the reservoir density of a state. So if we take the approximations in which the density of states of the reservoirs is small, like the smallest energy scale in the system, one can simplify the expression in which the occupations only contribute for Q equal to 0 and alpha equal to beta case. Now, once we have so this is basically the general expression for the occupation number, the different Fourier harmonics of the occupation number, where this U beta and U alpha are the Floquet modes in the system. B lambdas are the coupling matrices which connects the system with the reservoirs, and epsilon alpha, epsilon beta are the quasi energies of the system. Gamma alpha, gamma beta, and these are the terms which comes because the system is connected with the reservoirs. And the F lambda is the Fermi distribution function, which can be written in terms of the sums of the Mastrubara frequencies. Now, this is a general expression. And now if we take the limit, flat band limit, when the density of states of the reservoirs are constant, and the limit where the reservoirs are connected at every site of the system, plus the weak coupling limit when we take the rho r, which is the density of the states of the reservoirs, is very small, we get a nice analytical expression for the occupations of the Floquet state, which is given by this equation. And we find, similar to the static case, the occupations in the Floquet case is given by the summation on Fermi functions multiplied by the corresponding Floquet state weights. So once we get the occupation, the expression for the occupation, we define the current operators for the system, because like this is a general occupation which contains relaxation due to the particle tunneling to and forth to the reservoirs. And we define the current operator using the density matrix, and we get this expression. When we simplify it further, we find the second term in this expression can be given in terms of the quasi-energy derivatives with respect to the phase difference, and where the first term is again the occupations, the steady state occupations of the Floquet states. Now, to understand it further, this quantity, we know the mu r, which is the chemical potential of the reservoir, which is a variable. When we fix the value of mu r, where the mu r is like equal to the energy of the Floquet Majorana fermions, the quasi energies of the Floquet Majorana fermions, the maximum contributions only comes from the Floquet state. So for example, if the system is having the 0 modes only, then if I keep the mu r to be 0, then the only contribution in the current comes from the 0 Floquet states. And similarly, when the system is having the pi modes, if I keep the mu r to be plus pi or minus pi, the maximum contribution in the current comes from the derivatives. The maximum contribution in the current comes from the pi Floquet states. And to understand it further, in this case, we are plotting the quasi energies, like the quasi energy gaps of the Floquet modes with respect to the phase difference in two cases. In this case, system size is 25 and delta is greater than this omega j. And we find when the system size is small, the Floquet Majorana fermions, they never interchange the occupation at phi equal to pi phase difference. But in the other system size limit, when n equal to 65 and delta is lesser than omega j, we find there's an interchange in the occupation probabilities of the pi mode at the phi equal to pi phase difference. And this is the reason we get the sharp jumps in the current when the system size is larger, or in the limit when delta is less than omega j. And how much the difference is there, like if I call this as an unoccupied state having less occupation than this, and if I call this occupied state, then the difference between the unoccupied state and occupied state is not 1 or 0. What is the difference? It depends on the weights of the Floquet states of the Floquet Majorana fermions. Now, we define a quantity as a system is having the particle hole symmetry. This we can write the total current expression like in this form. So the first term is having the contribution from the positive energy state, and the second term is having the contribution from the negative energy state. Epsilon alpha bar is basically minus epsilon alpha. The system is particle symmetric. We can convert this delta epsilon alpha bar by delta phi with a minus sign of delta epsilon alpha by delta phi, and this quantity we call the occupation difference. So we get this expression where only the negative energy states, negative energy Floquet states contributes. And we define a quantity called summed occupation difference, in which we define the chemical potential mu r in terms of mu r plus k omega, and we do the summation on this k parameter. And we find when the system is having the Floquet Majorana fermions, this expression takes an interesting form given by this particular equation, where the first term is like the quasi energy of the Floquet states. Second term is the winding in the time phase, which goes to 0 in the Floquet Majorana fermion case. And the third term is the term which depends on the Fermi functions of these states. So we compute these summed occupation differences in two cases: when the system is having the 0 mode and when the system is having pi mode. And by solving this expression, we find in the zero temperature limit, the summed occupation difference for the zero modes are 1, zero Floquet modes are 1, and for the pi mode, the summed occupation difference in the zero temperature limit is -1. So similar to the static case, where like the occupied and unoccupied states, then the zero temperature limit shows a difference in the occupation plus -1. In this case as well, the occupation difference, summed occupation difference is quantized, and it takes values either +1 or -1. And similar to the summed occupation difference, we also defined the summed Josephson current, in which basically we are summing over all the Fourier harmonics of the chemical potential. And we get this expression where this is basically the quasi-energy derivatives times the occupations, Floquet occupations, the summed Floquet occupations of the Majorana Fermions. And we find similar to the static case, when delta n is -1, one can also, similar to the static case, when delta n is -1 and current is given by this expression, one can also write the similar expression for the Floquet Majorana Fermion case. For the summed Josephson current, in which this new f, which is the summed occupation difference, is either +1 or -1. And also there is one more change. In the static case, the current expression depends on the coupling parameters, and in the Floquet case, it depends on the modified coupling parameters. So this is basically the coupling parameters times some Floquet, the state weight of the Floquet states at the junction. And from this analysis, we get an interesting result, which is the sum rule for the Josephson current when the system is having Floquet Majorana fermions. Like when we sum over this different Fourier harmonics of the chemical potential, the occupation difference is quantized in both zero case and pi case. And similar to the static case, for the sum rule, the current expressions can be written only in terms of the quasi-energy derivative. So once after this, we have two methods to compute the current. One is like the current computation from the non-equilibrium Green's function techniques. This and the second is current computation using this occupation and the quasi-energy derivatives. And using these two ways, we can also compute the summed Josephson current. So in this plot, I am plotting the summed Josephson current with respect to the phase difference, computed using the non-equilibrium Green's function for a clean system, and also computed using the sum rule, basically the quasi-energy derivatives for a clean system. And we find these two results matches pretty well. And we also check the disorder dependence of these signatures by putting the static disorder in the system. So the screen plots are basically for the value of disorder 0.1, and again current computed using the non-equilibrium Green's function and using the sum rule. This is the next value of the disorder, which is 0.25, again the non-equilibrium Green's function and sum rule, then 0.35, 0.45. And we find these two results, like whether we are computing the current from the non-equilibrium Green's function or from the sum rule, it matches pretty well for all values of disorder. But the signatures, which shows the sharp jumps at phi equal to pi, which are the signatures of the Majorana fermions, these signatures are only there for small values of the disorder or weak disorder. Similar to this disorder dependence, we also compute the temperature dependence of this summed current. So till this point, we considered the temperature of this entire system was 0. And now we include the temperature dependence using the Fermi functions. And in this situation, we are plotting the current and the summed occupation difference for roughly zero temperature case. We find the Majorana signatures are there. It's like sharp jumps at phi equal to pi phase difference, delta n is 1. And then when we increase the temperature, we find, okay, the signature, this sharp jumps gets smoothing out, and also delta n changes the value from 1 to 0. This is again the next value of temperature, and then again the higher value of temperature, and we increase the temperature in terms of the quasi energy caps. So we are changing the temperature from 0 to some 0.5 delta J. Delta J is the quasi energy caps of the Majorana modes which are localized at the junction. This is when temperature is equal to delta J. So we find the 4-pi periodic signatures are there for small values of temperatures. We also now in the inside we are plotting the summed occupation difference at roughly close to phi equal to pi phase difference with respect to the temperature dependence. And in pi case, this was the analytical form we got. And if we compute the same thing numerically, we find these two expressions matches pretty well too. So this entire change in the occupation difference can also be understood analytically using this expression. So here with the slide, I summarize my talk. So when the system is having the time dependence, or i.e. Floquet systems are weakly coupled to the fermionic bath, the sum of the Fermi functions gives the occupation probability of the steady states. And this leads to an exciting form of summed occupation difference for the particle whole pair of excitations. And when the system is having the Floquet-Majorana fermions, this leads to a sum rule expression of Josephson-Current reminiscent of the static Majorana fermion-mediated Josephson-Current. And this especially recovers the jumps at phi equal to pi phase difference and the quantized occupation difference. And these signatures we also find are robust against this weak disorder and small temperature. So I would like to thank everyone for attending my talk, and then we can go with the question answer if there are any.
Hi, I have a question.
Yes.
Can you hear me?
Yes, I can hear you.
Yeah, just 3-4 slides back, you were telling that the signature of Majorana bound states you get by a sharp jump in the current. If you would please
Yes.
go back to the previous slide where you were showing with the disorder. Yes, disorder.
Disorder. Okay.
Yeah. So for a clean system, I understand, yes, there will be a sharp jump in the current. And for the disorder, for some 0.1, 0.25, there is no sharp jump. So is it
Yes.
like the presence of disorder affects the how to say? I mean, affects the signature of Majorana bound states? I mean, I don't see any sharp jump for any disorders here.
Yes. So when the disorder strength is weak, let's say some delta to be 0.1, there are roughly sharp jumps. But when the disorder strength is larger, some 0.45 or 0.35, there are no sharp jumps at phi equal to pi phase difference. This we can understand because this disorder, it mixes the different states like when the disorder is not there, the system is clean, and there is no interaction between different state having different momentum k and k prime. But when we are putting the disorder in the system, it sort of mixes the properties of the different states. So for the clean systems, the Majoranas are localized at the junction only. But when the disorder is there, the gaps, it also changes the quasi-energy gaps of the system. So this we can understand roughly it is equivalent to the changing the quasi-energy gaps in the system. So the Majoranas are not exactly at the zero energies when the strength of the disorder is large. So this can be a reason.
But in because I am asking because in reality no system is actually clean as far as I understand. There will be some impurity, some disorder in the system.
Mm-hmm.
So I don't understand. I mean, experimentally, I'm speaking. I'm thinking. I
Mm-hmm.
mean, if there is a disorder in a system, and
Mm-hmm.
according to your theory, if I
Mm-hmm.
have a clean system or let's say very small disorder, then I will see some Majorana bound state.
Mm-hmm.
But I don't know. I mean, for some higher disorder, it doesn't show such signatures. It is a bit. Yeah.
Yes, I mean, this is what we are getting. We are changing the
Mm.
disorder in terms of delta, which are the Floquet Majorana, the gaps of the Floquet Majorana states. So when the delta is like comparable, I mean, when the value of the delta is in comparison, it's comparable to the gaps, we find the signatures are not there. I mean, this sharp jumps, it gets smoothed out.
So, do you know? I mean, what will be the effect of the magnetic impurity on this plot? I mean, what kind of disorder you have taken here?
So in this analysis, we are taking the static disorder,
Hmm.
in which we are just putting the disorder in terms of this chemical potential. Like as the chemical potential is like on-site chemical potential is there in the system. Similarly, we are adding the static disorder, where like
Hmm.
every
Okay.
site is having some disorder.
Okay. So the okay. Yeah, okay. I get it. Okay. Thank you.
Thank you. So are there any other questions?
I'm
Okay.
sorry, but I have another question to ask.
Okay.
Uh, what is the temperature scale you have taken in this work?
So the temperature scales which we are taking,
Uh,
again, these are the plots which shows the temperature dependence of this Josephson current signatures. So delta J are the, again, the quasi-energy gaps of the Floquet Majorana fermions which are localized at the junction. And this is the temperature scale we are taking in this for the system, and it varies in units of delta J from some roughly 0 to 1. So it goes from 0 to delta J.
okay. Thank you.
Thank you.
Maybe I can ask a question. Can you hear me? Hello?
Yes, sir, I can hear you.
Oh, okay, good. Thanks for a great talk. So I was wondering what determines delta J itself? So
But
this is the gap at the junction between the Floquet Majoranas? What?
mhm.
Um,
Okay, so these gaps, which are like the gaps of the Floquet Majorana states, which are localized at the junctions, are determined by the system size of the superconductors. Like if we take we are taking two identical superconductors, only having two different phases, phi L and phi R, but length and every other parameters are same. So when the size of these superconductors are small, then the interaction between, okay, I should take the slide. Okay, so when the size of these superconductors are small, then these two Majorana fermions are not well separated. But when we increase the size of these superconductors, these two Majorana fermions are well separated, and these two Majorana fermions can be connected using the tunneling parameter. So the gaps delta J, which are the gaps of these Floquet Majorana states, can be controlled by the system size. It basically depends on the system size of these superconductors.
Okay, so it also depends on the coupling between the two.
Yes, sir.
Does it depend on the phase difference, or are you defining delta J at a particular phase difference?
The gaps delta J, it depends on the phase difference too. Uh, so So these are basically
Okay.
the plots for the delta J for the small system size and large system size with respect to a phase difference.
Okay,
And
good.
it depends on the phase difference.
Yeah, great. So that's why your occupation, when you have non-zero temperature,
Mhm.
starts to go through zero here because the gap is actually vanishing, right?
Yes, sir.
Yeah, good. Thanks.
Thank you. Are there any other questions? So if not, I would like to thank everyone for attending my talk. I also would like to thank this VSF, the Speakers Corner Talk organization, which gives us the platform to present our works. Thank you, everyone. Okay.